September 21st, 1942, and test pilot Eddie Allen stands on the tarmac at Boeing Field in Seattle, staring at something that looks less like an airplane and more like a promise someone made drunk. The first B-29 prototype looms before him, massive and strange. Its fuselage is bloated, grotesquely wide compared to the svelte B-17 flying fortresses rolling off production lines. The most unsettling part isn't what Allen can see, it's what he can't. Preparing and narrating this type of story took us long efforts and hard work, so if you are enjoying the story, please consider subscribing to our channel. Somewhere inside that aluminum skin, Boeing's engineers claim they've created 3 separate pressure vessels that will maintain sea-level atmospheric conditions at 30,000 feet. No oxygen masks, no heated suits, just shirt-sleeve comfort while Japanese fighters struggle to reach you through air so thin a man would pass out in 90 seconds. The Army Air Corps had asked for this, demanded it, actually, but nobody, not even Boeing's own engineers, was entirely sure it could be done. Pressurizing a single cabin like the 307 Stratoliner was one thing, 10 of those had been built. Manageable. Pressurizing 3 separate compartments in a combat bomber while it carried 5 tons of bombs and 11 crew members through flak and fighter attacks, that was gambling with physics in ways that made veteran aircraft designers nervous. Allen knew the risks intimately. He'd flown the 307 prototypes. He'd survived the testing of the second B-29 months earlier, when an engine fire nearly killed him and his crew. Now he was about to find out if WWII's team had solved problems that most aeronautical engineers considered unsolvable. The problem wasn't just pressurization, it was maintaining it. A bomber isn't an airliner. It has gun turrets that need to rotate, bomb bay doors that open at altitude, a crawl tunnel connecting forward and aft crew sections. Each one represented a potential leak point, a place where precious pressurized air could hemorrhage into the thin atmosphere, and if the pressure failed at 30,000 feet, the crew wouldn't have minutes to respond. They'd have seconds before hypoxia turned trained airmen into confused, dying passengers. Boeing's solution was sitting in that ungainly fuselage, waiting to prove everyone wrong or catastrophically right. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The path to this moment began not with the B-29, but with a civilian airliner that most people today have never heard of. Back in December 1938, while Nazi Germany prepared for war and America clung to isolationism, Boeing rolled out the 307 Stratoliner. It looked like someone had grafted B-17 wings and tail surfaces onto a fat tube with windows. That fat tube was the point. WWII, the engineer who designed Boeing's magnificent 314 Clipper flying boats, had become obsessed with a simple concept. If you could maintain ground-level air pressure inside an aircraft, passengers could fly above the weather in comfort. No more vomit bags during thunderstorms. No more flight cancellations due to icing. Just smooth sailing at 20,000 feet, where the air was thin and calm. The engineering challenge was deceptive. At sea level, atmospheric pressure is 14.7 pounds per square inch. At 20,000 feet, it drops to 6.4 pounds per square inch. That pressure difference wanted to explode the fuselage from inside like an overfilled balloon. The solution was making the fuselage perfectly circular in cross-section. A circle under pressure maintains its shape. An oval or square would distort, creating stress concentrations that would crack the aluminum skin. Boeing built the 307's fuselage in sections, each one pressure-tested at the factory by sealing it and pumping compressed air inside, while workers coated the exterior with soapy water, watching for bubbles that would reveal leaks. It was tedious, methodical work, but it paid off. When the 307 entered service with Pan American Airways in July 1940, it became the world's first pressurized airliner in commercial operation. But the 307 had limitations that made military planners nervous. The entire cabin was pressurized as one unit, from the nose to a pressure bulkhead just forward of the tail. Simple, clean, completely impractical for a bomber. A combat aircraft needed defensive guns. The B-17 crews manning those guns sat in open waist windows or cramped ball turrets, exposed to negative 40-degree temperatures and thin air that required constant oxygen mask use. Gunners routinely suffered frostbite on their faces and hands. Some passed out from hypoxia when their oxygen systems failed. In January 1940, the Army Air Corps issued specifications for what they called a superbomber. The requirements read like a wish list written by someone who didn't understand physics: 400 miles per hour speed, 5,000-mile range with bomb load, high altitude capability, and critically, a pressurized crew compartment. That last requirement changed everything. If the crew was pressurized, they couldn't sit in open gun positions. But if they weren't in the turrets, how could they aim the guns? The specifications essentially demanded that Boeing invent remote-controlled defensive weapons while simultaneously solving pressurization problems that had never been attempted on this scale. 4 companies submitted proposals: Boeing, Consolidated, Douglas, and Lockheed. Douglas and Lockheed quickly dropped out. The technical challenges were too severe, the development timeline too compressed. That left Boeing and Consolidated in competition. Consolidated would eventually produce the B-32 Dominator as a backup, but from the beginning, Boeing's proposal stood apart. Wellwood Beale, now Boeing's chief engineer, assembled a team that included Edward Wells, a brilliant 29-year-old designer who'd been with Boeing since he was 21. Together, they faced a problem that made the 307 Stratoliner look simple. They needed to pressurize not one cabin, but 3 separate compartments: the forward crew section, the rear gunner section, and the tail gunner's isolated position. Between these pressurized spaces would be unpressurized bomb bays and the wing structure. The tail gunner would sit completely alone, separated from his crewmates by an unpressurized section he couldn't access during flight. Why 3 compartments instead of 1? Weight and structural complexity. Pressurizing the entire fuselage would require reinforcing sections that didn't need pressurization, adding thousands of pounds of useless structure. By creating pressure vessels only where crew worked, Boeing could save weight for bombs and fuel. But this created a new nightmare. How do you connect the forward and aft pressurized compartments so crew can move between them? The answer was the crawl tunnel, a 28-inch diameter tube that would run 35 feet through the unpressurized bomb bay area. The tunnel itself had to be pressurized, essentially a long cylindrical pressure vessel suspended through the aircraft's center. It had to be strong enough to maintain pressure, light enough not to add excessive weight, and positioned so it didn't interfere with bomb racks or structural members. Boeing's engineers spent months calculating stress loads. The pressure differential would be trying to expand that tunnel like a balloon. If it failed in flight, both the forward and aft compartments would explosively decompress. At 30,000 feet, the crew would have less than 20 seconds of useful consciousness, not enough time to reach oxygen masks, don emergency equipment, or descend to survivable altitude. The forward compartment was easier to design because it followed the 307's proven principles: a circular cross-section fuselage with a pressure bulkhead at the aft end, just forward of the wing. This space would house the pilot, co-pilot, bombardier, navigator, flight engineer, and radio operator. 6 men working in shirt-sleeve comfort while outside, the temperature dropped to 50 degrees below zero. The aft compartment presented different challenges. It needed to accommodate the central fire control gunner, 2 side gunners, and a radar operator, along with the gun-sighting blisters that protruded from the fuselage. Each blister was a potential weak point, a curved plexiglass dome that had to withstand the pressure differential without shattering. Boeing designed them with layers of reinforced plexiglass, tested to failure in pressure chambers. Some exploded during testing. The engineers strengthened them and tested again. The tail gunner's compartment was the most isolated position on any combat aircraft ever built. A single man sitting beneath the rudder, separated from his crewmates by 60 feet of unpressurized structure, he entered his compartment before the aircraft pressurized, climbing through a hatch from the aft section. Once airborne and pressurized, that hatch couldn't be opened without depressurizing both compartments. If the tail gunner was wounded, His crewmates couldn't reach him until the aircraft descended below 8,000 feet. But the isolation brought comfort. While B-17 and B-24 tail gunners sat in cramped, freezing positions with oxygen masks freezing to their faces, the B-29 tail gunner would work in heated, pressurized comfort with enough room to actually move. The psychological toll of isolation was considered acceptable compared to the physical toll of freezing and hypoxia. Now came the truly hard part. Seals. Every rivet hole, every access panel, every point where the pressure vessel was penetrated represented a potential leak. Boeing's solution was obsessive attention to detail that bordered on paranoia. All rivets in pressurized sections were flush-mounted and sealed with special compounds. Access panels used rubber gaskets compressed by dozens of fasteners. Electrical cables and control lines passing through pressure bulkheads were routed through specially designed fittings that maintained the seal. The pressure regulation system itself was another engineering challenge. Boeing contracted with Air Research Manufacturing Company to design an automatic system that would maintain cabin pressure throughout the flight envelope. The system used compressed air bled from the superchargers on the two inboard engines. This air flowed through ducts into both pressurized compartments. Regulators automatically controlled internal pressure based on altitude. Preparing and narrating this type of story took us long efforts and hard work. So, if you are enjoying the story, please consider subscribing to our channel. From sea level to 8,000 feet, the system simply provided ventilation. No pressurization was necessary. All excess air escaped through relief valves. But from 8,000 feet to 30,000 feet, the regulators maintained constant 8,000-foot pressure inside the cabin. The crew would feel like they were cruising at 8,000 feet while the aircraft operated at 30,000, where most enemy fighters couldn't effectively engage them. Above 30,000 feet, physics imposed limits. The system could still compress air, but the differential became too great to maintain 8,000-foot pressure. At 34,000 feet, the cabin would experience 10,000-foot equivalent pressure. Still breathable, still comfortable, still infinitely better than the unpressurized hell of earlier bombers. Testing this system pushed Boeing's engineers to their limits. They built a full-scale pressure chamber containing a complete forward fuselage section. Technicians sealed themselves inside while external pumps simulated altitude conditions. They ran thousands of pressure cycles, looking for fatigue cracks, testing seal integrity, measuring air loss rates. Every failure was documented, analyzed, and corrected. The most terrifying test involved battle damage simulation. Engineers deliberately punctured the fuselage with various sized holes, then measured how quickly pressure bled away. Small holes, like those from rifle-caliber bullets, caused controllable leaks. The compressors could maintain adequate pressure even with several small holes, but larger damage, like a 20mm cannon shell hit, could cause rapid decompression. Boeing's solution was remarkably low-tech. They equipped each crew position with wooden plugs of various sizes. If the fuselage was hit, crew members would hammer plugs into the holes. It worked. B-29 crews would later report doing exactly this during combat missions over Japan, patching bullet holes with wooden plugs while maintaining pressurization and continuing to their targets. By August 1940, before the first B-29 had even been built, the Army Air Corps demonstrated stunning confidence in Boeing's design. They ordered 2,500 B-29 seconds straight off the drawing board, 1,664 aircraft on order before the prototype flew. It was the largest aircraft production commitment in history, dwarfing even the B-17 program. The Air Corps was betting billions of dollars that Wellwood Beale and his team had solved problems that didn't yet have proven solutions. General Henry Hap Arnold, commanding general of the Army Air Forces, understood what was at stake. War with Japan was looking increasingly inevitable. The Pacific Theater would demand bombers with range to strike from distant island bases. But more critically, those bombers needed to survive. Japanese fighters were nimble and deadly. The only way to defeat them was altitude supremacy combined with defensive firepower. The B-29's pressurization would provide that altitude capability. Construction of the first prototype began in September 1941 at Boeing's Seattle plant. Workers assembled the forward pressure vessel first, installing it complete with all internal structure before attaching it to the wing section. The precision required was unlike anything Boeing had attempted. Pressure vessels don't tolerate sloppy work. Every joint had to be perfect. Every seal had to function. Every rivet had to be correctly installed. The crawl tunnel installation was particularly nerve-wracking. It had to align perfectly with openings in both the forward and aft pressure bulkheads while threading through the bomb bay without interfering with bomb racks or structural members. Engineers used jigs to hold everything in position while welders sealed the joints. Then came pressure testing. Compressed air at 15 pounds per square inch differential. The tunnel held, no leaks. The team moved forward. Installing the aft pressure compartment required similar precision. The gun sighting blisters were fitted into their openings with special seals that had to compress evenly. Too much compression and the plexiglass would crack. Too little and air would leak. Boeing developed special torque specifications for every fastener, ensuring consistent compression around each blister. The tail gunner's compartment was assembled separately and installed as a complete unit. A single pressure bulkhead sealed it from the unpressurized rear fuselage section. Workers tested it by pressurizing it independently, checking for leaks around the entry hatch and the gun mounting points. By September 1942, the first B-29 was complete. Eddie Allen performed the first flight that day, a brief 30-minute hop that confirmed basic flight characteristics. But the real test was still ahead. Nobody had yet pressurized the aircraft at altitude. The system had been tested on the ground, but ground testing couldn't simulate the thermal stress of minus 50-degree outside temperatures combined with 70-degree cabin temperatures. Metal expands and contracts. Seals compressed at different rates than aluminum. Would everything hold together when subjected to real operational conditions? The second flight in October 1942 pushed to 15,000 feet with partial pressurization. Allen reported the system worked, but cooling the compressed air from the superchargers required more refinement. The air entering the cabin was warm, too warm. Boeing's engineers went back to the drawing boards, redesigning intercoolers and air distribution systems. Then came December 30th, 1942. The second B-29 prototype experienced a catastrophic engine fire shortly after takeoff. Eddie Allen fought to bring the burning aircraft back to Boeing Field, but the fire spread too quickly. The plane crashed into a meatpacking plant, killing Allen, his entire crew, and 20 workers on the ground. It was Boeing's worst disaster. The investigation revealed engine problems unrelated to pressurization, but it shook confidence in the entire program. With Allen dead and the second prototype destroyed, Boeing had to rebuild both its test program and its morale. The Army Air Forces, already committed to thousands of aircraft on order, had no choice but to push forward. Too much was riding on this airplane. Too much money, too many lives, too much strategic necessity. By June 1943, 14 B-29 service test aircraft were flying. These planes incorporated fixes from the B-29 testing and began exploring the aircraft's operational envelope. One test focused specifically on the pressurization system's performance at extreme altitude. A B-29 climbed to 35,000 feet and cruised there for an hour. The crew reported cabin altitude held steady at 8,000 feet. No leaks, no problems. The system worked. But working in test conditions isn't the same as working in combat. B-29 crews would soon discover that pressurization brought new challenges nobody had anticipated. When a fighter attack put holes in the fuselage, pressure didn't just disappear. It created whistling screams as air escaped at hundreds of miles per hour through bullet holes. The noise made radio communication nearly impossible. Crew members developed hand signals to coordinate during depressurization events. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Temperature management became another unexpected challenge. The cabin heating system was designed to maintain comfort at high altitude, where outside temperatures reached 50 below zero. But when flying low-altitude missions, the heating system would overwhelm the cabin. Crews learned to manually override the system, accepting some discomfort rather than roasting in what became flying ovens. The remote-controlled gun turrets, a direct consequence of pressurization requirements, proved revolutionary but complex. General Electric's central fire control system allowed gunners to operate multiple turrets from sighting stations inside the pressurized compartments. But the system required careful calibration. During early operational missions, gunners reported the turrets sometimes didn't track correctly. Boeing and General Electric engineers spent months refining the analog computers that controlled turret movement, compensating for airspeed, temperature, gravity, and parallax error. What made the B-29's pressurization system truly remarkable wasn't any single innovation. It was the integration of dozens of systems that all had to work together perfectly. The superchargers bled compressed air, the intercoolers cooled it, the regulators controlled it, the seals contained it, the heating system tempered it, and all of this happened automatically while 11 crew members focused on navigation, bombing, and fighting off enemy fighters. Boeing had created something unprecedented, a bomber that could fight at altitudes where the enemy couldn't effectively reach it, in comfort that allowed crew members to remain alert and effective for missions lasting 16 hours or more. The B-17 crews who transitioned to B-29 seconds later described it as moving from a cramped, freezing, exhausting nightmare to a spacious, comfortable environment where they could actually think clearly and work effectively. The psychological impact was significant. B-17 crews over Europe were exhausted after 5-hour missions. The physical toll of oxygen masks, heated suits, and cramped positions left men drained. B-29 crews flew 8 to 12-hour missions to Japan and returned tired but functional. The pressurization system didn't just keep them alive, it kept them effective. Production B-29 seconds started rolling off assembly lines in 1943 from 4 factories. Boeing's plants in Renton, Washington, and Wichita, Kansas, Bell's plant in Marietta, Georgia, and Martin's plant in Omaha, Nebraska. Each aircraft's pressurization system had to be individually tested before delivery. Technicians would seal the aircraft, pressurize it, and spend hours with soapy water and leak detectors, hunting for any imperfection in the seals. Quality control became obsessive. A single leak that went undetected could fail catastrophically at operational altitude. Boeing instituted multiple inspection stages. After initial assembly, the pressure vessel was tested. After installation of gun turrets and blisters, it was tested again. After final assembly with all equipment installed, a complete pressurization check at full differential pressure. Only after passing all tests would the aircraft be accepted by Army Air Force's inspectors. The first B-29 seconds arrived in India in April 1944 for Operation Matterhorn, the initial strategic bombing campaign against Japan. Maintenance crews in theatre had never seen pressurized aircraft. Boeing sent technical representatives to train them on system operation and troubleshooting. The representatives carried specialized tools and spare parts, pressure regulators, seal kits, bulkhead fittings, and those wooden plugs for battle damage repairs. Early missions revealed a problem Boeing hadn't anticipated. Flying through tropical weather, the aircraft would ice up differently than expected. Ice forming on the gun sighting blisters would sometimes crack the plexiglass. The temperature differential between the warm, humid interior air and the super-cold exterior created condensation that froze in layers. Boeing modified the heating ducts to blow warm air across the blister surfaces, melting ice before it could build up. Another issue emerged with the crawl tunnel. During long missions, crew members would need to move between forward and aft compartments. The tunnel was barely 28 inches in diameter. Men wearing bulky flight gear could barely squeeze through. Several crew members got stuck, creating panic until they managed to push through. Boeing issued guidance limiting tunnel use during flight to emergencies only. The tail gunner's isolation created psychological challenges that hadn't been fully appreciated during design. Some tail gunners reported severe claustrophobia, sitting alone in that small compartment for 16-hour missions. The sensation of being cut off from the rest of the crew, unable to move or interact, wore on men's mental resilience. Some crews developed informal communication methods, tapping Morse code on the pressure bulkhead or using the intercom constantly just to maintain human connection. But for all these challenges, the B-29's pressurization system delivered on its promise. By late 1944, B-29 seconds were routinely flying missions at 28,000 to 32,000 feet over Japan. Japanese fighters struggled to reach the altitudes. Even when they did, their pilots were exhausted from the climb, wearing oxygen masks that limited their effectiveness. The B-29 crews, meanwhile, were working in shirt-sleeve comfort, alert, and capable of defending themselves with the sophisticated gun system. The psychological advantage extended to the strategic level. Japanese military planners knew American bombers were operating above their effective ceiling. It demoralized the defense forces and emboldened American crews. The B-29 became known among Japanese fighter pilots as the aircraft they couldn't reach, couldn't catch, and couldn't effectively engage. By March 1945, General Curtis LeMay changed tactics, sending B-29 seconds on low-altitude night incendiary raids against Japanese cities. The pressurization system, designed for high-altitude operations, became less critical. But even flying at 5,000 feet, having a comfortable crew environment improved mission effectiveness. Navigators could plot courses more accurately. Bombardiers could focus on targeting. Radio operators maintained clearer communications. The system that had been designed for survival at 30,000 feet continued delivering advantages even at low altitude. The B-29 pressurization system's legacy extended far beyond World War II. Boeing applied the lessons learned to post-war commercial aircraft. The 377 Stratocruiser, derived directly from the B-29, used refined versions of the same pressurization technology. When Boeing developed the 707 jet airliner in the 1950s, the engineering team included veterans of the B-29 program who understood pressure vessel design, seal technology, and the importance of redundant systems. Every modern airliner flying today traces its pressurized cabin heritage back to Wellwood Beale's obsessive work on the 307 Stratoliner and then the B-29 Superfortress. The circular fuselage cross-sections, the attention to seal integrity, the automatic pressure regulation, the multiple safety systems. All of these became standard because Boeing proved they could work on a combat aircraft operating under the harshest conditions. The B-29 proved something that aircraft designers still reference. Complexity can be managed if the engineering is thorough and the testing is rigorous. The pressurization system was fiendishly complex compared to unpressurized bombers. It added weight, it added cost, it added maintenance requirements, but it delivered capability that fundamentally changed strategic bombing. That capability was worth every pound, every dollar, every hour of testing. 3 years and 960 B-29 seconds were built by war's end. Of those, pressurization system failures accounted for relatively few losses. Most pressure-related issues were minor leaks that crews could manage with those wooden plugs. The system's reliability vindicated Boeing's approach of exhaustive ground testing before operational deployment. By August 1945, when B-29 seconds delivered atomic weapons against Hiroshima and Nagasaki, the pressurization system had become so routine that crews barely thought about it. They climbed to 30,000 feet, maintained cabin comfort, dropped their weapons, and returned home. The system that had seemed impossible in 1940 had become invisible by 1945. The best engineering always does. Wellwood Beale retired from Boeing in 1964, 30 years after joining the company. He'd overseen the design of the 314 Clipper, the 307 Stratoliner, and the B-29 Superfortress, 3 aircraft that pushed aviation technology into realms that had seemed unreachable. But when asked late in his life what he was most proud of, Beale would point to the B-29's pressurization system. Not because it was the most glamorous achievement, but because it solved a problem everyone said couldn't be solved at that scale, under those constraints, with that timeline. The impossible had become routine, and, somewhere over the Pacific in 1945, 11 crew members sat in shirt-sleeve comfort at 30,000 feet, breathing normally, working effectively, completely unaware they were benefiting from an engineering achievement that would shape aviation for the next 80 years. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.